And just note that this webinar kicks off an online training workshop. And basically that doesn't mean you have to be online. Oh, still forgot to change that. Not from now through February 4th, from now through June, June 4th, June 3rd. So this is the first of two kind of strongly suggested live webinars. And the second one, you get to choose from times on May 19th and 20th. And then we have some optional live interaction times during Wednesday, Thursday, Friday, May 25th through 27th. Erica will be hosting office hours, and you can have a personal tutorial. And then the last week of the period during which we're hosting this training workshop, we'll have a wrap-up webinar, which is for answering questions and sharing ideas about how people will implement. So the expectation for your participation is that, including these live webinars, you'll spend some time over the next couple of weeks logging on to the YouthAstroNet community, introducing yourself on the forums. We have discussion forums, and I'll show you how to do that during this webinar, taking images with our telescopes and posting them to that online community. And so you are the learners especially for this first part of the workshop. This week, we don't want you to be thinking too much about how will you do this with your students. We want you to kind of feel what it's like to be brand new at this and be learners yourself. So the centerpiece of YouthAstroNet is our MicroObservatory robotic telescope network. And this is a network of telescopes that are you and your students control over the internet. There's no human in the loop. You tell the telescope what target you want it to point at, and you set some parameters for the cameras of the telescope, exposure time and filters. I'll show you that today. And the next day, you get that image back. These are two telescopes on the left in Arizona at the Smithsonian's Whipple Observatory. Actually, if you look, I don't know if you can see, there's a little white dot right on the top of that mountain, and that's the giant telescope that the professional astronomers here use at the top of that mountain. We're at the base camp of the observatory. And over on the right, you'll see one of our telescopes on the roof of the building where Erica and I are sitting right now. And we have some students in that image from the Timothy Smith Network, of which Owen's a part, who took a field trip here and got to chat with Frank. Part of the YouthAstroNet program that's spreading across the country is to offer those of you who are far away opportunities to have virtual tours with us and interactive Q&As with scientists here using the same technology we're using now. And we'll talk about that as we go through the training as well. So, how do you get access through the telescopes? Well, here's where things are a little bit different for those of you who have experienced Youth Capture the Colorful Cosmos. We have a different portal to the telescopes that's customized for the YouthAstroNet community, and that's what I'm going to show you today. And it ends up offering some additional opportunities for kids and reducing some hassles for educators, we hope. So I'm going to show you how to get onto the portal. Oh, here, actually, I'll come back to this about the telescope in a moment. Well, let's find. So there's two ways to find the link to the YouthAstroNet portal. And those of you who have used MicroObservatory before may be very familiar with the web URL microobservatory.org. And microobservatory.org gets you to this page, but these are past programs have used these portals. At the bottom, you see this special little link, secret little link to the YouthAstroNet portal. That's what will get you to the YouthAstroNet program. And you need to have an account for this. Erica is sending you all the information for your accounts, and you'll see that there's actually 3 YouthAstroNet portals. One is the main portal for all activities using the telescopes, and that's the portal the youth will only use. But we have a special portal just for educators, just for you guys, and that's the portal on which the current training is going to take place. We have forums just for educators to share information in the Educator portal. And then we are working on a parent portal that parents of your students would be able to access information about supporting kids in STEM, kind of general information, and some activities that they and their kids could do together. But we haven't quite, there's nothing in there yet. That's a future evolution of the program. I'm going to first, I guess, log into the Educator portal quickly. I'm already logged in, but you would be, when you click on that, you'll be asked for your username and password, which Erica will send you. And you'll see that we have this checklist and all these things that this is only for you educators. And over the next 3 weeks, you'll be exploring all these areas of the Educator portal, which will prepare you by the end of this workshop. You'll have enough information to be able to plan and kind of think about how you're going to implement the program with youth. And the program, as I mentioned in the pre-training webinars, is very adaptable. So there's lots of different ways, lots of different projects students can pursue using the telescopes. So my job today is to teach you how to use the telescopes through this portal. And the telescopes, remember, are not in the Educator portal. They're back here in the Activity portal. I'm going to click there. So this is what students will see when they log on. And you'll note that students can earn badges. This is something that will be evolving too as we grow the program. As they complete certain projects, they earn badges. You'll see over on the right, latest news, things and recent activity, things that have happened since you last logged on will show up in these windows so you can keep up to date if there's anything new. But down at the bottom, and you can see I have a little notice here that there's been 4 posts in the astrophotography forum since the last time I logged on. Down here at the bottom, however, these blocks are the various tools and challenges for students to pursue activities. This is the block you will be using most. This is where the interface to the telescope and the interface to image processing software is going to be. So I'm going to click on that, and you'll see there's 3 different main telescope tools. There's the image request site, and it will look familiar to those of you who've used MicroObservatory.org before. This is how you tell the telescope, I want to look at the moon tonight, or whatever it is you want to look at. Then there's an image archive, your own personal image archive. So if you tell the telescope to look at an image of the moon, tomorrow in your YouthAstroNet account, that image will be sitting in your own archive. You don't have to go off and look for an email. You don't have to figure out where that file is. It's going to be sitting right in your account. And then this third tool, which I'll also be showing you today, is the image processing tool, which is new to MicroObservatory. So those of you who have used the image processing tool that you had to load onto a machine, this is a browser-based tool. it crosses many devices. You can use it on iPads or Chromebooks or whatever it is. So it's much more usable for educators in a wide variety of situations. And it happens to be the same tool that the professional astronomers use here at the observatory. The students are using the same powerful software that the professionals use, so they learn lots of skills. But we've modified it to be a little less overwhelming for students. All right, so let's first figure out how to get an image. I clicked on request an image, and you'll see it's a very easy interface. There's a selection of targets categorized to objects in the solar system, stars and nebula, which are outside of our solar system, but still inside of our Milky Way galaxy. And one thing to be aware of, that both adults and kids often, it's easy to be confused about what's the difference between a star and a planet, a star and a galaxy. So we have some resources to help kind of explain those astronomy vocabulary terms, and to really understand that the universe is organized into solar systems, which are planets going around stars like our sun. Then there's galaxies full of gas and dust and stars with their little planets. And then there's billions of galaxies. And there's a nice work kind of reference called Cosmic Cast of Characters in your Educator portal that can help keep track of all the categories of objects. All right, who would like to type in the chat box a target you would like to observe, or you would like me to observe, since this is my account we're looking at? As soon as I see something appear in the chat box, we'll go look at that target. Whirlpool, Sarah wants to look at the Whirlpool galaxy, all right. So here that is here. So if I click observe, I get an interface that asks me to set 3 settings for the telescope. One is field of view, and the Whirlpool galaxy only offers 1 field of view, although some objects offer a zoomed in field of view or a wide camera field of view. And what that's really telling you, that 1 degree, is telling you that the normal mode of our telescopes, the picture that you get back, is a square degree on the sky. And what's a square degree? What does that mean? Well, if you hold your pinky at arm's length, and from the top to the bottom of your pinky, if you had a string coming out from your eye, one to the top of your pinky, and another string coming out from your eye to the bottom of the pinky, that tiny little angle would be 1 degree, you know, out of 180 degrees, which would be the whole sky. So our telescope looks at a little patch of the sky that you could cover up with your pinky finger. That's what that's telling you. So we'll choose the 1 setting here. We have an option for exposure time, which is telling the telescope there's a digital detector inside the telescope, and the exposure time controls a mechanical shutter. Actually, I can show you a picture of that shutter if I'm going to move that out of the way. So field of view is telling how wide a piece of the sky you're looking at. The exposure time is sending a message to a mechanical device inside the telescope that's going to open for however many seconds you say, let light in, and then close in order to expose the digital detector that's at the focal point of these telescopes. All the astronomers here at the observatory, none of them look through eyepieces anymore. They all control telescopes remotely, whether those telescopes are in space or whether they're on a mountaintop. And the telescope has a digital detector, which is really the technology that everybody's got in their cell phones now, but it was first developed for astronomical uses. Okay, so let's go back to our Whirlpool galaxy. And so galaxy is pretty dim. So you need to let light in order to let enough light in for the detector to see it. Yeah, so Sarah notes that if you click on this, you get a hint. Image may be underexposed, optimal, image may be overexposed. So in general, we actually kind of, although it's a teaching moment, the way our system works is typically our telescopes don't take images if students request a really short exposure time, because if you think about it, we'd be using 3/4 of our telescope time. 3 out of every 4 images would be a bad image. And so that's kind of a waste of the telescope time. So we try to provide guidance for what the optimal exposure time is. But it's always good for kids to keep track of that, because then they'll see patterns where if you are taking a picture of the moon, 45 seconds is definitely not the optimal exposure time. 0.1 second, a fraction of a second, is optimal. So, and this target, the Whirlpool, doesn't give a selection of filters, but some targets allow you to set a filter inside the telescope in front of the detector. So when you ask for a red filter, there's a little wheel in the guts of the telescope that will turn and put a red filter over the detector. So the shutter will open and the light will go through the red filter. And during webinar 2, which is next week, we're going to really focus on light and color and how these colored filters can help you figure out what color the universe really is. But we're going to wait till next week for that. Okay, whoops, wrong, what about in there? Okay, let's go back to our real request. So I'm going to hit continue. And those of you who've used MicroObservatory before, you know, you don't have to put in your email address because you're on your own account. And you see right here, Whirlpool Galaxy was requested for M. Dussault. And it says, click here. That's how I can get to see the images I've requested. So I am going to click there now. And you'll see this is my personal, in Mary's account, my list of images that I've requested over the last couple weeks. So I've got a bunch. A few have failed. Once in a while that happens. Various things happen where the telescope doesn't take an exposure. And you'll see that I just asked for the Whirlpool Galaxy. And so that image is pending at 45 seconds through the clear filter. And tomorrow, hopefully, I won't get a failed, but I'll get a collected. And that image will be waiting for me in my account. So you are sending a request to a real instrument. If it's cloudy tonight, you're going to get clouds in your images. That telescope's going to point at the sky, light's going to come in, bounce off the mirror, bounce off the secondary mirror, go through the filter wheel, go through the shutter, onto the detector. Okay? And if it's cloudy, these telescopes are actually weatherproof, unlike they were custom built at the Center for Astrophysics here, so that people who are astronomy novices wouldn't have to worry about, oh, well, am I allowed to open the telescope tonight? Is it too cloudy? These are very robust and they're weatherproof. So the only thing is if the skies are cloudy, you'll have clouds in your images. Okay, so let's go back to my, where did it go here? My, sorry, I lost my archive. Here we are, and there's my sun, my Whirlpool galaxy that I just asked for. So you have these in your archive, you have each image is linked. And I'm not going to use these links right now, but you can explore that when you get online. The left link links to the public image archive of the MicroObservatory telescopes. And that's a separate website outside your account. But it's a way to get at all the images our telescopes take, whether they're part of this program or not. So that's interesting to explore. And then this link opens up that image in our image processing tool. This is one way to open it, but I'm actually going to show you the second way to open it, which is to go to the image processing tool. Remember, you get to that here, okay? And here is where this is a browser-based image processor, so you don't need to open up any new software. I guess I want to, is that big enough on your screen? I could go one bigger maybe, and so people can see it a little better. All right, so we'll see if that's okay. So when you first open up, there's no image loaded. You've got a blank screen. When you guys first log in, you'll have in your account a list of archived images. Those are in everybody's account. So even before you ever use the telescope, images will be loaded that you can explore. And that's really good sometimes if you're doing a summer camp and it's the first day and kids haven't taken their images yet, but you want to show them how to use the telescope, you already have a bunch archived. And I'm actually going to open one of those, which is the moon image. Okay. Well, if you've paid attention to the moon this week, this obviously isn't a moon that was taken this week. It's archived from a while ago. And in fact, each image, the name of the image has a code in it that tells you exactly when that image was taken. This image was taken, the first two are the year in 2015, so last year, on September 28th at 4:47 and 12 seconds. So exactly when this image was taken, although that 04 is in universal time. So one of the things students may start to explore is the difference between the time indicated in the image, the time it was in Arizona when the image was actually taken. Astronomers have to think a lot about time. So, all right. We have an image of the moon, and we have all these tools at the top that allow you to manipulate that image. And so I'm going to show you a few of these tools now. But there are many. We're creating video tutorials to help you understand how to open image, how to process it, how to do different things. Some of those video tutorials are already online in the youth activity portal, and Erica will be creating some as well. So I have my image of the moon. I guess I want to show you some of the simple things that do what you would expect them to do. So I can zoom in to a moon that's twice as big, or a moon that's twice as big 4 times, or a moon that's twice as big, or 8 times the size. And you notice now you're starting to really see the pixelated quality of this image. Now, a nice tool, let's say I want to get over to another part of the moon. There's something called a panner that allows me to pan this zoomed in image. So I'm going to click on that, and a little pop-up window comes up. And so and you can even move that. So you can see this dark dot in my full image is this right here. Okay, and I want to get to this place down here. It looks really interesting to me, so I'm going to do that. Oh my goodness! All right, so it's much brighter here, right? So each of these individual square dots is a pixel or picture element, and all digital images these days on the web and everywhere are made up of pixels, picture elements, and in data from a telescope, these picture elements are actually direct indicators of how much light was coming from the object at each point. So they're mathematically accurate. Astronomers use them to make measurements of the brightness of objects in space. And so if I move my cursor around this image, actually, I can't, here we go, there we are. So I move my cursor around this image. I want you to look at these numbers right down here, okay? So you can see the pixel value changes. If I go up here where it's dark, the pixel value is 2400. If I go down here where it's bright, the pixel value is 3946, and the physical location is really just the XY position of my cursor on the screen. So I want you guys to direct me. This is going to be, we'll see if we can use the chat box in an interesting way here. I want you to direct me and my cursor to where you think the brightest pixel is. So you're going to say up, up, right, right, left, up, down, to get my cursor to the right place. So if anyone wants to tell me what direction to move. Up, okay, how about, all right. Now where? Is that going to be the brightest? Which way? Where do you think the brightest pixel is going to be? Right, okay. All right. How about now? Do I need to go further right? Or up or down? More right, yeah, okay. So you're all obviously looking at the same spot I'm looking at, which is right in here. And you notice that in this region of the moon, look at the pixel value. I'm moving my cursor around, and it's staying at 4095. And it turns out that the detector in the telescope, its maximum brightness value for any pixel is 4095. So once you get that much light, the image becomes overexposed at that point. And you can't, that's why you want the right exposure time. If you open the shutter for too long, all of your pixels would be at 4095 and you wouldn't see anything. Okay. So that's great. You guys are getting very good at understanding the math behind the images. I'm going to go back and reset my Zoom. And oh, actually, let me go back. I wanted to show you one more thing, which is this tool, which is a great tool for explaining what a digital image is. And actually, I'm going to go to my, hang on. Right, so we just explored some pixels. Whoops, here we are. So really, each of those little squares has a number associated with it, which is directly related to the amount of light that fell on the physical detector inside the telescope. So here's a simplified, the MicroObservatory detector actually has 650 by 500 pixels. Here's a 10 by 10 detector, and you see that there's a lot of light here, a lot of light here, and these pixels here have a lot of light. whereas this stripe up here has very little light. And so if we visualize that in different shades of gray, if we paint by number so that the brightest places are white, the darkest places are black, and everywhere else is in between, that image, and if I go back, you might have been able to see that. There's the one eye, the other eye is bright, the smile is bright. So basically, image processing is a way of assigning brightness color values to numbers that are the signal that comes back from the telescope. Okay, let's go back to our moon. And I wanted to show you this pixel table tool, which is the really cool thing. So if I hover my cursor around these, I don't know if you can see that, right? In this bright blob, that pixel is pretty bright, 39,000. But up here in this darker circle around it, it's 33,000. If I go up to that really bright blob, whoops, sorry, where you guys were, you can see all these pixels are saturated at 4,095. So that's a way to see the math behind the image as well. We set the zoom. Now, the neatest thing about the image processing tool is that students can enhance and colorize their images using features up here in the software. There's many different color maps, and I'll explore those in a minute, and using these tools, which basically change how the computer assigns colors, whether it's shades of gray or shades of the rainbow, to brightness values. So in fact, you can see if this low brightness value, if I bring that up, it's saying, this is telling the computer any pixel that's 655 or lower, color it black. And so the background here is all at 350, so that's black. If I bring it up further, well, now there's all these are kind of low. I can actually, if I bring this up further, oh, see, all of these are anything with a brightness value lower than 1900 is being colored black, and that's a lot of these dark areas of the moon. So using these and the high brightness limit, only things that are 4,095 are colored exactly white. And so that's that area there and there. If I bring this down, now things that are only 2,900 are being colored white. And so you don't get as much detail. You're getting all washed out because all that detail that's in those different brightness values is being washed out. So these are very useful to getting the image to look the way you want it. And we have two new features that professional astronomers use that were never available before in MicroObservatory. And these are called stretch or contrast, stretch and squeeze, and shift. And to show you how these work, I'm actually going to, right now we're using a color palette of 255 shades of gray, which is what black and white computer monitors use. So you can see down here, it's telling you that anything 3,589 or above here are these very light shades of gray. Things in the 1200s are pretty dark. Things below 800 are nearly black. I'm going to use a color palette that has only, instead of 255 shades of gray, it has only 8 colors. All right? So here you get a lot less nuance, a lot less detail, because everything's binned in 8 shades of color. Well, 9 if you include black. And so if now I'm going to, I'm going to squeeze, I think. Wait, am I? Uh-oh. Let's try that. Is this going to work? All right. What's going on? Oh, there we go. So stretch and squeeze. When I move this to the right, I'm squeezing all the different colors into a smaller relative values. Here I'm spreading them over more values so I get more detail. Squeeze, stretch, squeeze, stretch, squeeze, stretch, right? And then here, let me squeeze. Oops, what happened? There we go. This is a tool that kind of shifts those colors to different regions. So watch, I'll click on this one click at a time. You see how the way the colors are mapped to different values is shifting and shifting the other way. So these tools offer you very fine control over how you want to colorize your image. And they also have a lot of math behind them in terms of really all image processing is paint by number, and it's all assigning different colors to math, to different mathematical values. Okay. Let's see, where am I? I got so well. So we have lots of different colors. Many of them have many different, so here's one called Fire Sky. Does anyone see anyone here you'd like to try? If you type it in, we'll try it out. Luke, great question. Why is the coloring so important to astronomers? There's a couple reasons. One is actually aesthetic, and in fact, all the Hubble Space Telescope images that get produced and sent out over press releases, astronomers know that in order to have people pay attention to their findings, they want the images to be stunning. But a more scientific reason is that different ways of visualizing your data brings out different physical characteristics in the object that you've taken an image of. So if I'm really interested in these rays that come out from this crater, I see that I've picked a color palette here where I can actually measure those, right? In fact, I'm not quite sure how to show you how to do this, but let's see if I make a little box and I want to measure the length of one of these rays in pixels, right? I could do that. And so this particular color palette that I've used really highlights that. In fact, if I might, see, I'm kind of dimming it out there. Whereas here, these rays really come out, but these don't. Let's say I wanted to study this crater. Well, then I want something like that, which is bringing out the details there. So, Luke, the choice of different colors brings out different features which may represent the thing you're studying. Okay, great question. I'll leave it to you all to explore the color palettes on your own. So I kind of wanted to do this introduction on an image like the moon, but it can get much trickier when you have objects that are very dim in the sky. And so I'm going to close this. Actually, I'm going to leave it open, but I'll I'm going to open an image of a dim object here, which is, oh, I don't know. Let's try my Trifid Nebula here. All right. So here is an object that pretty much looks like nothing's in there. But remember, if we bring down that high brightness value, okay, bringing it down, there's a bunch of dim stars in the image that are now coming out. And now I just start to see something that right here. I don't know if you could see, but there's a very dim cloud of gas right there. And that's the object of interest that the telescope was pointing at, even though when you originally opened up this image, it looks like that. Right? It looks like there's nothing in there. So a lot of times, kids will take an image of a dim galaxy or a nebula, and they'll use the colors, and it looks really neat with these colors, but they haven't really brought out the object of interest because it's so dim. They just have a bunch of dots on the screen. That doesn't mean there isn't something there. So I'm going to show you a trick that is the key trick to know if you have a really dim object. I'm going to go back into grayscale here. And that is this. Right now, you see that we've set, the highest brightness value here is at 1515, and the lowest is at 180 here. And these different shades of gray are split evenly across that. That's called a linear color table scale. But you could also, and we just found out that there's a dim, you could see when I brought this down here, that way down in the 200s, right? There's something in there. And so if you have your thing set up like this, the 200s are all black, right? So there's a kind of scaling called log scaling, where now one of the things you see is that these are not evenly spread. You get lots of shades of gray for a very small window of brightnesses that are low, and only a few shades of gray for the really bright stars and things. Well, that still doesn't look great. I understand that. So here's the second part of the trick. First, you'll do log scaling, as I did. And secondly, the thing that's really dim along with our nebula is the night sky itself. Because as I move my cursor around, if you look down here, you'll see the night sky isn't 0. It's like 317. There's some light coming from the sky where there's no stars. So to get your best contrast between the night sky and that very dim nebula, what you want to do is find that value, which is 300, and you want to set your low brightness limit to 300. Watch what happens. Whoops, that was too far. I have to go exactly at 300, and I can actually type it in, 300, and hit enter. Now watch, when I hit enter, watch what happens to that nebula. Right? Pops right out, because the nebula is only 325. It's only 25 brightness values brighter than the dark night sky. And so, but this log scaling gives you lots of levels of gray. So I'm not sure, now that's a lot of math. I've gone over a lot of things. Log scaling sounds so, it can be a little overwhelming, and I don't want it to be that way. I just wanted to show you some tricks for bringing out dim images, and note that you have a lot of control in trying different settings, right? So that's a key thing to practice here. All right, so I really like the Blend Rainbow palette. And again, we can shift and stretch those values there or find them. So what time have we got here? Okay, I just have a few more minutes. I want to make sure. So you're now you've got this great image. You want to save it. I want to note that one other neat thing you can do is add text. So if you go to region, you can add a circle. If I want to, I want to highlight. This is my, whoops. This is my object here, and I want to add some text. I do that with this text region. I double click. And I can type Mary's Trifid Nebula in Rainbow Blend Palette color table. Okay. And then I have to click Apply. Okay, there, now it says it. Close that. And I can make it a little bigger. Like this. I can even give it a little jaunty angle, like that. And now I want to save this. I love this image. I want to save it and I want to post it to show you guys in the forum. So I'm going to show you how to do that because this is your assignment after this webinar. You're going to create an image you like and you're going to post it in the forum. So I go to image and I'm going to save as a PNG. Next week we'll talk a little bit about FITS, which is the special format that astronomers use for astronomy images. And next week we'll go over why that's special. But when you want to save an image to post on a website, you want to just save it as a PNG file. So I'm going to do that. And when I click on that, you can't see on the webinar, but my computer is grinding while it calls up a window asking me where do I want to put that. There we go. So I'm going to put this image right on my desktop, and I'm going to call it Trifid Webinar 1. Okay. So now if I just open it, and whatever, there it is. I've downloaded my image. I have it on my device now, on my desktop. And so now I want to post this image in the forum. So I'm going to go back to the main page. And actually, I don't want to post it in the youth activity portal. I want to post it in the educator portal for all of you. So I'm going to go back. This is a breadcrumb, get you back to the YouthAstroNet page. I'm going to go to the educator portal. And here's the forum, request and process an image. So this is your assignment, and I'm going to do it now. So you see that I've created a post that says, May cohort, post your first images here. All right. And we'll click on that. And I did an earlier webinar. So the first webinar I did the Orion Nebula. But now let's stick in my Trifid Nebula that I just did. So I don't know if you saw what I just did. Let me cancel that. Oops, I don't know how to cancel it. One of these links said reply. So I clicked on reply and this opens up. So I'm going to type in. So here is an image of the Trifid Nebula that we made in the webinar Thursday evening. Okay, hit return, and now I want to insert that image. I click on this little mountaintop icon. I can also color my text and make it bigger or smaller, use different fonts. This is a regular text editor, so you can do that kind of stuff. So it brings up a typical window when you browse something and you're uploading to the web. So I'm going to go find that TRIFID image, choose file, and go to my desktop. That's where I put it. And there it is, TRIFID Webinar 1. And if you don't type anything in here, that's fine. It'll save it as TRIFID as what you've named it before. But if you want to change its name, you can do that as well. Upload. All right. So here's my image. If I just click insert, it gives me a little flag. Are you sure you want to continue without including an image description? Without it, the image may not be accessible to some users with disabilities. So most images on the web now have you put a caption on them, so a screen reader or something like that can tell somebody who's, so I'm going to type in TRIFID Nebula. Okay. Now I'll insert. There it is. Okay, so I've made my post, but you know what? I'm taking up a lot of room. That's going to be kind of big on the page. So I think I want to shrink my image, and that's very easy to do. I'm going to click on my image. I'm just going to shrink it. Okay, and if you wanted to add another image, you could do that right in this same post. It's best actually not to attach. You don't want to use the attachment thing to add an image, because then it doesn't show in the forum and people have to download it. You really want to insert it using that little mountain. And then I hit post to forum, and there's my post. So your mission now, we've been through all we've been through a lot in this tutorial. Again, there are video tutorials for the things we've just done. And we'll also put a recording of this webinar online. But that's kind of your first introduction to the workshop portal and to the MicroObservatory telescope and image processing tools. So you'll see that over the next couple of weeks, there's lots of things for you to explore. This part of the Educator portal above the line are the things that constitute the online training. Below are all the resources for you to implement with students to explore. So actual lesson plans, and curricula, data collection sheets, things like that. As we move on through the webinar, you'll be exploring those as well through the training. Examples of student capstone projects are here, and ideas for sequencing, because remember, it's very adaptable what you want to do with the YouthAstroNet resources. You could do a summer camp where kids just learn to create their own images and then create a astrophotography display. That's actually the core of the Youth Capture the Colorful Cosmos program. So here's a example of a student exhibition of their own images. But you might decide that you actually want students to explore an object of interest in space. So some of them explore the moon and they do some web research and then they learn some stuff about the moon. Others explore galaxies, and then they create their own wikis, their own web pages using, and that's their capstone project. So the portal also has and we'll explore that next week during the webinar next week. We'll actually create a wiki page during the webinar so you can see how that's done. Okay, let me go back. Oh yes, right. Yeah, JS9, because it's JavaScript, actually, yeah. So again, as I mentioned, the tools you're using, JS9 being one of them, are used by the professionals here at the observatory. And Joe DePasquale is actually the science imager for NASA's Chandra X-ray Observatory. And he is actually one of the STEM mentors. He is available for interactive Q&As. He's got a post on the youth portal. You see this area of scientists and experts. Joe gave us information about himself, and there's even a video about the work he does. Kids can explore. All right, let's see, let's go through. So I'm really gonna go very quickly. Kids could explore the moon phases. They could take images of Jupiter, and Jupiter's moons move at different times, and they can see that. They can take images of the sun and observe the motion of sunspots. I'm just giving ideas for projects, and we have lots of them. They can also explore size and scale using the image processing tools and taking images of different objects. Unlike images in textbooks or on the web, all the images students take are taken with the same instrument. So this image over here of the moon, there's actually, I superimposed an image of Saturn, and it's right here. So the MicroObservatory telescopes are not great planetary imaging telescopes, except for the moon, because planets appear very tiny in the field of view, because it has a pretty big field of view so that it can fit things like globular clusters and deep space objects that are very big in the sky, but you need a lot of light. So Saturn, we know, is a lot bigger than the moon in real life, right? Saturn is much bigger than the moon, but in MicroObservatory it appears much smaller because it's so much further away. And you can actually use the pixel length of the moon versus Saturn to calculate exactly how far Saturn is away. And if any of you are interested in that, we can do extra tutorials on how to do that. So here's a range of objects near and far, all taken with the same camera. So this is actually how big on the sky these objects are in comparison to each other. All right, so again, very adaptable how you decide to implement YouthAstroNet. The key elements are for your students to learn how to control the telescopes and how to manipulate and learn from the images that come back from them, and then to create some capstone project that can use their engineering skills, their art skills, their communication skills, their teamwork skills, and build skills as they create some project that tries to convey what they learned in pursuing it. Okay, any questions? Best practices for getting their images printed. Yeah, actually, I think some of our Youth Capture the Colorful Cosmos experts probably have different strategies that they've used. In fact, I'm actually going to unmute people just in case anybody has something to say about that, Lisa. Okay. Does anyone want to pipe in about how you printed your images?
Sure.
Well, go ahead, Sarah.
Yeah, so I bought glossy photo paper and just borrowed the printer of an architect who's on our board. And we printed them out in 11 by 14. It used a lot of ink, but because it was on photo paper and he had a pretty nice printer, they turned out pretty great. And it wasn't all that difficult to do.
Well, one way I did it was just when they saved it as a gift, just printed it.
Right.
A gift.
Just using like a laser printer or something?
Yeah, HP LaserJet, yes.
Okay, that we've got.
Yeah,
And really, an inkjet printer will work just fine,
exactly. Yeah.
especially on glossy.
Color, you use color, not the black and white, but you know. I mean, the kids are learning, so you know. I mean, if we were like at NASA, we might probably want high resolution, but you know.
Yeah. Now, sorry, I'm hearing an echo of myself, so I had to turn folks off for a second. I do want to point out one thing, which is that because of the resolution of the telescope, remember it was only 650 by 500 pixels, so it's much less resolution than your own iPhones these days. The special thing about the telescope CCD detector is not that it's high resolution, but that it is responsive to very, very dim light, which iPhones are not. So the images don't really take great enlargement. And 11, you know, you can see in this exhibit here and the one I showed earlier that, you know, 8 by 11 or 11 by 14 is really probably the largest that you want to print out the images. Great. So, great. Next steps. Log on, and Erica will send you a PDF checklist, but the key things to try and do before next week's webinar are to use the Introduce Yourself forum to tell other educators who weren't on this webinar who you are and what kind of youth program you run. To request an image, process at least one image, and post it on the forum, and ask any questions as well. And so we'll be monitoring that. We look forward to the interactive discussion. And we'll see you. Well,
the checklist is already on the